speaker is Ramon van Handel from Princeton University, and we are very happy to have him here. His first talk is on vector concentration inequalities.
Thank you very much, Matthew, and thank you to Yogesh and all the organizers. And you know, it's a really great pleasure to be here in Bangalore with you. It's been a long time since I've actually traveled and gone places, you know, with the pandemic. So it's lovely to be in a room with lots of people. So I'm giving a board talk, so please interrupt me if you have any questions. You can do it anytime. So I'm going to talk about vector concentration inequalities. So these are certain questions related to concentration of measure. So what I would like to do is to start by reminding you or telling you, if you've never seen it before, what concentration of measure is actually about. Right? So everybody who's ever taken a course in probability or in statistics knows the law of large numbers, right? If I take many independent copies of a random variable and I average them, then if the number of random variables is large, this is close to the average, to the mean of the random variable, right? This is the law of large numbers. Now, this is central to our interpretation of probability theory, right? I mean, the expectation of a random variable is what happens when you average many independent draws from that random variable. On the other hand, you know, what's an average, right? 1 over n, sum k is 1 to n of xk. This is some linear function of a bunch of independent random variables, right? Now, in many problems in probability theory, you're not interested in linear functions, you know, in sort of more complicated problems, you will often encounter nonlinear functions, right? So you might want to ask the same question about nonlinear functions. Let's say I give you some arbitrary nonlinear function of a bunch of independent random variables, or maybe dependent random variables. When can we guarantee that that nonlinear function is close to its mean, right? Just like in the law of large numbers. And the theory of concentration of measure gives you very, very powerful tools that allow you to establish such type of conditions under which such type of things happen, right? So you can imagine it's kind of a nonlinear extension of the law of large numbers, and such principles are very powerful because they're used as tools inside the proofs of lots of other types of phenomena. Right? So let me give you the prototype. So there are many such theorems, you know, the entire textbook's written about this, but let me write down so that we have something to talk about, a prototype of what such a result looks like, right? So here is one of the simplest concentration inequalities. So this is for Gaussian random variables. It's called the Gaussian Poincare inequality. Okay. So suppose we have a bunch of independent standard Gaussian random variables, right? So they're Gaussian with mean 0 and variance 1. And now suppose I give you a nonlinear function from Rn to R, right? So this is a nonlinear function of these Gaussian random variables. So I'm often going to abuse notation, right? So when I'm going to view this as a random variable, let me write it down here maybe. So if I write f, I'm going to often identify f of g1 to gn, right? Whenever it's, you know, whenever it's clear from context, I'm going to view the function as a random variable where I plugged in the independent random variables that I'm interested in. Okay, so what does the Gaussian Poincare inequality say? It says that the distance of this random variable from its expectation, so this nonlinear function, right? The nonlinear function, how far is it from the expectation in mean squared? Well, it's upper bounded by the sum from I is 1 to n of the expectation of the derivative of the function with respect to the ith coordinate squared. Yes, this is the Gaussian Poincare inequality. And the first thing that you should notice about this inequality is that it has an equality case for linear functions. Or let's say gi to gn, g1 to gn is sum I is 1 to n, xi gi, where xi, right? So anytime I have a linear combination of the Gaussian, right, these functions are linear functions, then this inequality is actually an equality, right? Because on this side, df dgi is just xi, right? So on this side, I have the sum of xi squared, right? And this is what? It's the variance of a sum of independent random variables, right? Which is the sum of the variances, which in this case is also the sum of xi squared, right? Now that linear case is just the law of large numbers, if you will. Now for Gaussians, of course, you don't need the law of large numbers, right? But I took the function 1 over n, sum I is 1 to n of gi, right? then this inequality would show that the variance of that function would be bounded by 1 over n, which is exactly what the weak law of large numbers say, right? Which goes to 0 as n goes to infinity. So you should think of the linear case of this inequality as being the law of large numbers. But this inequality holds for arbitrary nonlinear functions, right? And therefore it gives you a very far-reaching extension of the law of large numbers. There are many nonlinear functions for which the right-hand side over here is small. And for such nonlinear functions, we also know that the value of the nonlinear function is close to its expectation in mean square and therefore with high probability. Does that make sense? So this is a prototypical example of an inequality that you see in the theory of concentration of measure, and its power lies precisely in the fact that it applies in an extremely general setting. Now, of course, this is just one inequality, and there's a whole theory surrounding such kinds of inequalities. So there are many extensions. So, first of all, this inequality is about Gaussian random variables. But of course, in many situations, we might not be interested in Gaussian random variables. We would be interested in other kinds of distributions, right? So, in fact, there are many such inequalities that hold for different types of distributions. So, for example, for product measures, if you have general independent random variables that are not Gaussian, there are many analogs of such inequalities. There are analogs of such inequalities under curvature assumptions. And these kind of things I'm going to talk about a little bit later in the talk. But these kind of conditions are very natural. They arise from differential geometry. But in fact, you know, they capture things like log concave measures, right? Measures whose density is log concave. That's a kind of curvature assumption. Or, for example, the uniform distribution on a manifold with positive curvature. These type of situations, which are dependent typically, they are not independent coordinates, but they're dependent, also satisfy such inequalities. There are many such inequalities for spin systems, for example, in statistical mechanics, or for random fields of various kinds. There are such inequalities on finite graphs. Right, I have some finite graph and I take a function in the finite graph. I take the uniform distribution over the vertices. I want to know whether it's close to its mean, et cetera, et cetera. Okay, so there's a huge set of results that looks like results like this, but for different types of situations. And of course, what varies in these results is exactly what do you mean here by the derivative, right? For example, if you're on a finite graph, then instead of taking the derivative here in the sense of calculus, right, you will take the difference between the function at a vertex and the function at its neighboring vertices. That will be like a derivative on the graph, right? So typically when you vary the situation, you will get different kinds of derivatives that show up on the right-hand side, but it's the same phenomenon that's really going on in all of these kind of examples. Now, beside that, we may not just be interested in the variance of the function, but also in other, you know, for example, higher moments, right? Tail bounds, right? Higher moments. This chalk, there it is. Moments, tail bounds, etc. So there are many more powerful versions of these inequalities that bound, for example, the probability that f minus the expectation of f exceeds some level, right? There's all sorts of inequalities like this that give more detailed information about the fluctuations of these random variables. But for our purposes, let's think about such inequalities in this way, right? Because this is not the direction that I want to go, okay? So this is a very, very quick introduction to the idea of concentration of measure, okay? And the basic question that I want to ask in this talk is there some sort of meaningful analog of these kind of results for functions, right? You see, these functions over here are real valued functions. So this is like a scalar random variable, right? Now, it's natural to ask whether there's an analog of such phenomena when your function is vector valued. So it takes valued in some norm space. Okay? So I don't mean here Rn with the Euclidean norm. I mean here some norm space. So any space with a norm on it. Okay? So who cares, right? That's always the first question you should ask when somebody tells you what they're working on, right? I mean, when I write something like this, it looks like abstract nonsense. You know, we could do it for scalars. Now we do it for vectors. You know, so what, right? But in fact, you could argue that this question is much more interesting than the question over there, right? Because many objects that we see in probability theory are not scalars, right? For example, I'm interested in random matrices, right? No, random matrices are not scalars. They're matrices, right? So what if I take a function of a bunch of Gaussian random variables that takes values in the matrices, right? An arbitrary nonlinear function. Then I get some sort of nonlinear model of random matrices. Well, I might want to know whether that random matrix is close to its expectation in the sense that the, let's say, operator norm between the function and the expectation is small. Right? It's a very natural question. Let's say you're interested in graphs, right? Well, you might take a function that takes value, you know, from a bunch of independent Gaussians that takes functions in the graphons. On graphons, there's a natural norm called cut metric, cut norm. If you don't know what it is, it doesn't matter. My point is that in different areas of probabilities, one studies different kinds of objects, right? These objects are typically not scalars, right? You're typically interested in some sort of interesting object, maybe high dimensional. And so it seems natural to capture the fluctuations of such random variables in some very general setting like this, right? So there are many types of questions that you can formulate in this way. And I'm actually going to give several examples of this throughout the rest of the talk, some of which you cannot see yet right now that are connected to geometry, but we will see this later, okay? So there are other reasons to study such questions. But even if you're just interested in classical probability, you can already see that this situation over here is much richer than just studying scalar random variables. Right? So this is the question. Now, the first question you should ask when I write down this question is, how would you even formulate such an inequality, right? What is a natural way to formulate such a phenomenon, right? So, okay, let me do something which I've always hated when I was a student. I'm just going to take the result we already have and I'm going to edit it, okay? So this is a scalar, right? Example, G1 to Gn are independent random variables, right? Now we take a function which takes values in some norm space. Now this is some norm on X, right? Now, what? Well, here we had these are real valued, they are absolute values. What's the most obvious way to turn it into a normed inequality? Well, everywhere where you see one bar, you're going to replace it with two bars. Now you have a vector valued inequality, right? Yes. Good. Vector valued inequality. Right? If the talk would now have been over, we would have all been able to have tea, right? But question mark. Right? It's such an inequality too. But this is, of course, the most obvious, let's say in the Hamming distance, this is the most obvious analog from the previous inequality. I only had to add 4 bars to the picture, and now I have a vector valued inequality, right? Question is such an inequality true? Right? Gaussian. So f is f of G1 through Gn if I don't. But f takes values in some arbitrary norm space. So it's from the Gaussian, it's a function of Gaussians. The question was, what is the expectation with respect to? So I forgot it. You told me that I have to repeat the question. Yes, that's f. Whenever I don't write anything, I mean it's a function of whatever random variables I'm working with, right? So here there are Gaussians, later on we're going to work with other random variables, but just because it takes a long time to write all of this, I often just drop this when it's sort of clear. But this function takes values in x, right? Right? So it's a function from the Gaussians to x, so it's random, so it's a function of these random variables, so I take the expectation with respect to G1 to Gn, and the output of the function is a vector, so I have to take a norm in order to be able to take the expectation of it, right? Okay. So this is the most obvious vector valued extension of the inequality I wrote down before. The question is, can such a thing be true? And the answer is no. Such an inequality is not true. It's just not true in general. In fact, it's not even true for linear functions, right? Remember that for the scalar inequality, linear functions were equality cases, right? But in this vector valued setting, this function is already false for linear functions, okay? So let me give you an example, right? Suppose that we take x to be L1. This is the L1. So this is just Rn with the L1 norm, right? So the norm of a vector x is sum I is 1 to n of the absolute value of xi, right? And what function are we going to take? We're going to take the function from G1 to Gn that just takes G1 to Gn into a vector. right? This is a linear function of G1 to Gn, right? So what is the L1 norm of f minus the expectation of f? This is just sum I is 1 to n of the absolute value of Gi. Well, this is of order n, right? This object over here is of order n. So in this example here on the left-hand side, we have n squared. We have something of order n squared, because I have a square here, right? What's inside of order n? I have n squared. But what's df dgi? Df dgi is just a vector that has zeros everywhere except in the ith coordinate, right? And the norm of this vector is 1, right? So the right-hand side here is sum I is 1 to n of 1, which is n. Right? So in this inequality, I have n squared on the left-hand side and I have n on the right-hand side. Such an inequality cannot be true, right? Is it clear? Okay. So the most obvious inequality that one can write down just turns out to be false when I take a general norm space. Right? And in fact, it's already false for linear functions, which were the equality cases of the inequality I wrote down before. So in fact, I want to make a bigger argument. What is difficult about this story? So forget for a moment about what's on the right-hand side here, right? Even if we look at the object on the left-hand side, right? So more generally, so any norm, let's say that I take x is Rn, and I take this to be any norm, okay? So a norm can always be written as the supremum, so the norm of x can always be written as supremum of some I is 1 to n, xi zi, over some z in some convex, symmetric convex set, let's say B, some set. This is by duality, this is always true, but in any case, this always defines a norm, okay? You can easily see that, right? So if I have an inequality for an arbitrary norm, right? Then what's on the left-hand side of this inequality, if I were to choose f to be the same f as over there, right? G1 through Gn, the left-hand side of this inequality would be the expectation of the sup over vectors in an arbitrary convex set, right? Of some I is 1 to n, zi gi squared, okay? This object over here describes the supremum of any Gaussian process, okay? Any Gaussian process can be expressed as a linear combination of Gaussians over some set. This is a classical fact. And therefore, even if I were to restrict to linear functions, the left-hand side of this inequality that I'm trying to estimate captures as a special case, right, the supremum of any Gaussian process. There's a huge number of ways in which these things can behave. It's known that the suprema of Gaussian processes is a very complicated object. There's not just one, there's a general theorem that characterizes them in a very complicated way. It's called the majorizing measure theorem of Talleyrand, but it's not usable in specific situations, right? So it seems that already the left-hand side of this inequality is so rich that it can capture almost arbitrary behavior. And that's for linear functions, right? So how could you possibly hope to have a general inequality for nonlinear functions, right? When already for linear functions, it seems that you can have arbitrarily complex things that can show up on the left-hand side of this inequality. Right? So these are some sort of general philosophical considerations, but from these considerations, you might be led to guess that this is a hopeless question, right? This question for general vector-valued functions is much too rich of a setting in order to be able to say anything meaningful, right? Really what one should do is for every kind of norm, right? For example, if the norm is a norm on matrices, we should study random matrix theory, right? If the norm is a norm on graphs, we should study random graph theory, right? The norm is a norm on whatever your favorite object is, right? We should study the theory for that favorite object, right? I'm asking here for a completely general theory that captures all these things in one theory. It seems kind of hopeless, right? So that's somehow the natural expectation. Once you start thinking, at first it sounds like a good question, but once you start thinking about this question more deeply, you start realizing that this question is so rich that it seems somewhat hopeless to have a general theory that characterizes all the possible situations you could have. Now, it turns out this is not true. So there is a completely general theorem that captures the behavior of concentration of these type of functions. The problem with this intuition is that we asked the wrong question. Okay? So I'm now going to write down the fundamental theorem of concentration of measure for vector valued functions in the Gaussian case. And this theorem is due to Pisier in the 1980s. But it is not very well known, even though it is a very powerful theorem, and its proof is only 3 lines long. Okay. The main point of this theorem is to ask the right question, to understand what kind of inequality to have. So let's again take G1 to Gn to be independent Gaussians, but let's take another set of them, which are independent copies. Right? So G1 to Gn and G1 prime to Gn prime are all independent standard Gaussian variables. Okay. And now we take a function f from Rn to any normed space. Okay. Then we have the following inequality. So the expectation of the absolute value of f minus the expectation of f. For this inequality, it is not important that we put a square here. You can put any power here that you want, p greater than 1. Okay. Is less or equal some constant. The important thing is this constant doesn't depend on the function. Okay. Times the expected norm of sum I is 1 to n of gi prime times df dgi p. So let's parse this inequality. Right? So rather than having on this side, let's say if p was 2, rather than having on this side the sum of the derivative, the norms of the derivative squared, what we do is we take the directional derivative of the function in the direction of an independent Gaussian vector. And we take the norm of that. Is the formulation clear? Okay. Now, the question is, what is this inequality? I mean, when I first write it down, it looks a little bit strange. But this inequality has a very crucial point, okay? Which is that if you look at this quantity over here, right, it involves g and g prime. But g is independent of g prime, right? So conditionally, on g, this is a linear function. Right? If I just condition on g, g is fixed. If I fix the value of z, g, these are just a bunch of vectors, right? For each I, this is just a bunch of vectors in x. And this is a linear combination of gi prime times some xi's, right? Some vectors in x. So this is a linear function of g prime, right? So I just told you that the complexity even of linear functions, of the norm of linear functions, is too complicated to say anything meaningful. But this inequality says nothing about the complexity of what happens for linear functions. This inequality up to the constant actually is equality for linear functions, right? Because if I were to take a linear function, right, sum I is 1 to n, gi times xi, where now the xi are vectors, right? So it's a linear function, a vector value linear function, right? Here I have the expectation of the norm of sum I gi xi, right? But here, df dgi is xi. So here I would have the sum of I gi prime xi, which is the same linear function. I just put in a bunch of different Gaussians. So for linear functions, you again have equality except for the constant. Okay. So unlike some other inequalities you might conjecture for the right-hand side, this inequality says nothing about linear functions. And that's as it should be, because linear functions, there is no general theory that allows you to explain how linear function behaved in different norm spaces, right? Linear functions, right, that are matrix valued behave like is studied in random matrix theory. Linear functions that take values in graph forms behave like is studied in random graphs, right? Linear functions that take values in some other space behave like whatever that area of probability is. You can't unify every area of probability in one theorem, right? But what this inequality allows you to do is that if you were to understand for a particular space x, if you were to understand the behavior of linear functions, then what this inequality allows you to do is to take that understanding of what you have over here on the right for linear functions and automatically upgrade this to an inequality for nonlinear functions. So the way that you should really view this inequality is as a linear to nonlinear principle. Right. So the behavior of linear functions is problem specific. But once you understand the behavior of linear functions, right? Then you can just plug that behavior into the right-hand side. You just apply whatever you understand about the behavior of linear functions conditionally on G over here on the right-hand side. And then you upgrade however you know linear functions behave, you automatically upgrade this to a statement about completely arbitrary nonlinear functions. Right? So you automatically get a nonlinear extension. So this inequality allows you to understand the behavior, reduce the understanding of the behavior of nonlinear functions to the understanding of the behavior of linear functions. And that transference doesn't depend on what norm space you work. Right? But for each individual norm space, you would have to have a theory that explains how linear functions behave. Right? And that's the right way to think about concentration of measure for vector valued functions. Right? So just like classical concentration of measure is some sort of nonlinear extension of the law of large numbers, right? Vector concentration inequalities is a sort of nonlinear extension of the behavior of linear functions, right? Vector valued linear functions. There's no general theorem that explains the behavior of vector valued linear functions, but there's a general principle that explains how to pass from linear functions to nonlinear functions. Is it clear? So let me just give you two quick examples. So one example, maybe I should just go back here to this example here. Let's go back and edit this example. So remember our first guess over here was that this would be a good inequality, right, for vector valued functions. And I showed you a counterexample that this is not true, right? Why is it not true? Because for linear functions, right? So if X is Rn, so if we work on an n-dimensional space, but with any norm, right? If this inequality were true, right? If this inequality were true, and we take a linear function, right? F of G is this G1 to Gn, if I take a linear function. Or more generally, maybe let me take a more general linear function. If I take a linear function, xi gi, right, where xi are in x. If I take a linear function, then if this inequality is true, what would this imply for this particular function, linear function? Then this would imply, then on the right-hand side I have that the expected norm of sum I xi gi squared. Right? Here we'll allow a constant, right? And on the right-hand side we have sum I is 1 to n, the norm of xi squared. Right? So if star were true, then just by plugging in linear functions, we will get this condition, right? And the counterexample I gave was to say that if the norm is the L1 norm, then this condition is false, right? Therefore, the star cannot be true. Right? Well, normed spaces that satisfy such an inequality for linear functions, they are understood. This is a very important condition in Banach space theory. It's been studied for functional analysts for at least since the 1970s, if not earlier, because this condition says when is the parallelogram identity that holds in Hilbert spaces true for a Banach space, for a norm space. So this condition says that the parallelogram identity for Hilbert spaces is true with inequality in this direction, right? And X that satisfy this condition is said to have type 2. So not every space is type 2. For example, if you take the L1 norm, we just saw that this condition is not true. So the L1 norm is not true, right? One norm doesn't have type 2. But for example, this condition is true for Hilbert spaces, right? Because of the parallelogram identity. So Hilbert spaces have type 2. But in fact, there are many norm spaces that are not Hilbert spaces that also have type 2. Okay, so this is a known condition in the theory of functional analysis, right? And so this condition is certainly a necessary condition for this nonlinear inequality, right? This condition is a necessary condition for that nonlinear inequality because if you apply this nonlinear inequality to linear functions, you just get this, right? But because of Pisier's theorem, we know that this is actually if and only if, right? Because suppose that you have a space that satisfies this linear condition, right? Then what we would do is we would just apply that linear condition over here, right? I condition on G and just view this as a linear combination of these vectors with coefficients Gi prime. If I apply that type 2 inequality over here on this side, we get that this side is bounded by the expectation of some I is 1 to n of the norm of the derivative squared. And that's exactly the inequality star, right? So this inequality star implies some special constraint on the norm space, which is known in functional analysis, but the converse is true by Pisier's theorem. Once you know that you have such an inequality for linear functions, then Pisier's theorem automatically upgrades this to a statement about arbitrary nonlinear functions, right? And therefore, we now understand, because of Pisier's theorem, that this nonlinear inequality is actually equivalent to its linear counterpart. And that completely characterizes when such an inequality holds, for which norm spaces such an inequality holds. Does that make sense? And you similarly have other types. For example, type P is the same thing when you replace here 2 by P. And similarly, you show that, the same argument shows that that's equivalent to such an inequality where the power 2 is replaced by P, et cetera, et cetera.
And Pisier's theorem will also get you the extra constant you will gain, right?
Okay.
Exactly.
So the question is about the constant. So the constant here is called the type constant of the space X, the type 2 constant of the space X. This is a name. So a space of type 2 has a type 2 constant, which is the smallest constant that holds here. And Pisier's theorem will show you that the constant you get in this inequality is exactly this constant times, let's say, pi over 2 squared or something like this. So up to a universal constant, it's the same constant that appears in both inequalities. So you do lose a universal constant, but you can't have everything. Actually, the constant of Pisier's inequality is sharp, but let me not go there. It turns out that this constant pi over 2 cannot be improved. There is and there's a very simple example with p equals 1, but let me not, you can ask me later if you want. So this is one example. And now let me just very, very quickly just, I mean, it's almost obvious, but let me just sketch again an example to random matrices. So suppose that I have some function from Rn to the space of d by d matrices, maybe with complex entries. Okay. So for every G1 to Gn, it spits out some matrix, right? So you can view this as a random matrix whose entries are arbitrary nonlinear functions of a bunch of Gaussian random variables. This is a highly nonlinear model of random matrices. It looks nothing like the models of random matrices we usually consider in random matrix theory, right? Typically in random matrix theory, you have to have some structure of the entries, right? But here, I mean, you can take each entry to be an arbitrary nonlinear function of a bunch of Gaussians, right? Now you might want to know how close is that random matrix to its expectation, right? So we might want to take here, let's say, for example, the operator norm, the largest singular value, right? So it's a very natural question, right? What can we say about the expectation of f minus the expectation of f in operator norm, right? Well, what does Pisier's inequality tell us? It tells us this is bounded by pi over 2 times the expectation of the norm of some I is 1 to n of gi prime times df dgi. So now what's the point of this inequality? Well, you see, if I condition on G, then these guys over here become just a bunch of deterministic matrices. So this is a linear combination of deterministic matrices with Gaussian coefficients, right? So conditionally on G, the object inside here is a Gaussian random matrix. Well, for Gaussian random matrices, we have many tools in order to understand their operator norm. I actually just talked about this in Delhi earlier this week. right? We have the non-commutative Gaussian inequality. We have our new inequalities that we developed using free probability theory. There are many tools we have to study the norms of Gaussian random matrices, right? So this theorem of Pisier doesn't tell you how to study random matrices. It has nothing to do with random matrices. But what it says is that any inequality for Gaussian random matrices, no matter what it is, this principle allows you to deduce from an inequality for Gaussian random matrices an inequality for random matrices whose entries are arbitrary nonlinear functions of Gaussian. Right? So it's just for free. It's a black box. You put in a result for a much simpler object, a Gaussian random matrix, and it spits out a general theorem that holds for extremely nonlinear models of random matrices. Right? Any inequality you prove for Gaussian matrices implies an inequality, a nonlinear inequality. Right? So this shows you, in what sense this is a powerful principle. But at the same time, the principle itself says nothing about random matrices. How could it? It has nothing to do with random matrices. Okay? Good? All right. So far, everything has been Gaussian. Right? But I told you that, Gaussians only go so far. Gaussian distribution, of course, is rather interesting. But nonetheless, most distributions in probability theory are not Gaussian, right? And most type of problems you might encounter in probability theory would not be for Gaussians, right? So it's a completely natural question once we understand the existence of such a theorem and what is the right way to formulate it, whether such theorems hold more generally, right? And what one might really hope, right, dream of, right, what we would really dream of is that there is a kind of theory of these vector-valued concentration inequalities that parallels the classical theory of scalar concentration inequalities. Right? The theory of concentration inequality is a huge theory, it's extremely powerful, it holds in many different settings. It would be beautiful to have a vector-valued theory that's inspired by this theorem of Pisier that allows us to do something similar at the same type of level of generality as the classical theory. Right? And unfortunately, until recently, there were 0 other examples, okay? So the proof of Pisier's inequality, I'm not going to do it here, but you can look in Pisier's original paper. It's not a paper, it's a set of lecture notes. The proof of this inequality takes 3 lines, and it's completely special to the Gaussian distribution. It uses very heavily the rotation invariance of the Gaussian distribution, which of course doesn't hold in any other situation. So you can do this proof. I mean, this proof is easier than almost any other proof in the theory of concentration of measure. You can do it in an undergraduate probability course. But it is completely special to the Gaussian distribution. Right? And in fact, already in Pisier's, Pisier is he's an analyst, okay? And his motivation for studying this was not the type of motivation I gave you over there. And I'll explain in a moment what his motivation is. But already in Pisier's original work, he didn't actually care about the Gaussian distribution. His real interest was not about Gaussians, but was about the next best thing, which are random signs. Random signs are they're even older than Gaussians. Bernoulli studied random signs in the 1700s, right? So the question, which was explicitly studied by Pisier, but actually dates back to the work of Enflo in the 1970s, is there an analog of, vector-valued concentration inequality for functions f that take values in the set of vectors of random signs? Right? So rather than putting in Gaussians, we put in random signs with the uniform distribution . So we take IID random signs, probability 1/2 of being +1 or -1. Rather than Gaussians, we just take a bunch of random signs, right? Maybe even simpler example than Gaussians, right? And of course, I have to explain to you what is this derivative, right? Because here we have df dgi. That doesn't make sense when you have a function on a discrete set. But you just replace the derivatives with the discrete derivative, with the finite differences, right? So instead of the derivatives, you would look at the discrete derivative. Right, so you take a function of the random signs, and then what you do is you just do it minus where you flipped the sign of the ith bit. And it's customary to divide by 2. But this is not going to make any difference for us. So rather than having a derivative with respect to the ith coordinate, you just take the difference with respect to the ith coordinate of the 2 possible values of the sign. That's called a discrete derivative in the ith direction. Right? Now, this is the natural notion of derivative on a discrete set. Yes?
Inequality, it looks like the Efronstein inequality, right? But the derivative is sort of this discrete derivative that you're taking.
Yes. So the question is that the question here is that this looks sort of like Efronstein inequality, right? And indeed, we're asking here: is there a vector-valued Efronstein inequality? Right? That's the question. And that was the original question that was that was asked by Pisier. That's what he was really trying to prove. And it dates back to an earlier question of Enflo in the metric theory of Banach spaces. And I want to take a moment to explain to you this application that they had in mind, because this is a typical application. So like many of these kind of theorems, originally these theorems did not come from probability theory, but they came from the study of analysis and geometry. And I think it's interesting to explain how, what kind of implications these kind of theorems had, if they were true, to the study of metric geometry. So here's one example. So Enflo had various different applications of these things. Let me give you like one of the simplest applications due to Enflo, right? So if such an inequality were true in whatever sense or another, so Enflo's question was not about such an inequality, because such inequalities had not been invented yet. Enflo's question was really close to the original question I had, which is, can you replace in the Poincare inequality the absolute values by norms, right? Now, it is necessary to be type 2. I argue that it is necessary for the space to be type 2, because for linear functions, that's type 2. But the question was, is it also sufficient, right? So, if true, right, if there is such a vector inequality, right, if there is a vector-valued concentration inequality for the discrete cube, right, then that would mean that X has type 2 if and only if you have this analog, right, less or equal up to some constant, some I is 1 to n, of the expectation of now the discrete derivative squared, right? This is the nonlinear analog of type 2, right? So we saw that Pisier's inequality says that if this is a function of Gaussians, right, then type 2 is equivalent to having this inequality with the regular derivative. If we now take a function from the discrete cube, if we had a vector concentration inequality that's just like Pisier's inequality, then that would also imply the analog of that statement that X is type 2 if and only if you have such an inequality for function on the cube. Okay? So who cares, right? Well, such inequalities have very strong consequences about embeddings of metric spaces. Okay? So you should think about the discrete cube, so sequence of random signs, as a metric space. Okay? The metric is the so-called Hemming metric. So you can think of this, for example, as a graph, minus 1, 1 to the n. You can think of it as a graph where two sequences of random signs are adjacent if they differ in one coordinate. Okay? So the distance, the natural distance on this set, just the distance between two random sign vectors is the number of coordinates in which they're different. Does that make sense? That defines a distance, right? So now you might ask, this is a metric space, right? And you might ask, suppose that I can take a map from this metric space into a Banach space, right? Can I create such a map so that the distances are approximately preserved? Okay. So you can think of a map F from the discrete cube to X that preserves distances. What does it mean? It means that the distance between F of epsilon and F of epsilon prime is lower bounded, let's say, by the distance between epsilon and epsilon prime. And it's upper bounded by some constant times the distance between distance and epsilon prime. Okay? So D is a constant that's greater or equal than 1. And if you have a map like this, this is called a bi-Lipschitz embedding of the discrete cube into the space X with distortion D. So D is the distortion. If D is 1, this is an isometric embedding. It preserves distances, right? If D is some constant, let's say 2, then all distances are preserved by this mapping up to a constant 2, right? One of the basic questions in metric geometry is which spaces can be embedded in which other spaces, right? So it's a very natural question to ask whether the discrete cube with its natural distance, right? The distance between epsilon and epsilon prime is the number of coordinates in which they differ, can be embedded in a Banach space, right? Let's say of type 2, right? So let's see what this, suppose this inequality is true. Let's see what it would tell us, right? So we take such a function f. This is a bi-Lipschitz embedding with distortion D, right? This is called the distortion factor, okay? So suppose you have such a map. So on the one hand, what can we say about the norm? So the norm of f minus the expectation of f, okay. So by Jensen's inequality, this is greater or equal the expected norm of f of epsilon minus f of epsilon prime. Sorry, is this, I'm using Jensen's inequality in the wrong direction here. Okay. Up to a factor 2. Let me put it. Because you see, I can just add and subtract the expectation of f inside, and then apply the triangle inequality, right? So maybe the factor 4. It doesn't matter. So if you have a bi-Lipschitz embedding, this would be greater or equal the expected distance between epsilon and epsilon prime, right? Now these are two sequences of random signs that are independent of each other. So two sequences of random signs that are independent of each other differ in about n over 2 coordinates, right? So this quantity is of order n squared, right? On the other hand, what do we have on the left-hand side? You see, this is really a kind of analog of the example that I wrote before. What do we have over here on the right-hand side of that inequality? We have the norm of DIF, right? Right, but DIF, remember, this was 1/2 times the norm of f of epsilon minus where I flipped the ith coordinate, right? This means that I flipped the sign of the ith coordinate, right? But epsilon and epsilon where I flipped the sign of the ith coordinate differ in only one coordinate, right? So the distance between these two vectors is 1, right? So if I plug in this distortion factor, this will be upper bounded by the distortion factor over 2 times 1. Right? So you see, if such an inequality were to hold, then the left-hand side would be lower bounded by n squared, and the right-hand side would be upper bounded by n, right? Because there's sum of n terms times d over 2 squared. Or d, let's say d squared, right? Because I have the square of this times n, because I have n terms, which means that the distortion would have to be at least square root n, which shows that in a very strong sense, the discrete cube cannot be embedded in a space of type 2. Because if such an inequality were true, then any map, right, any bi-Lipschitz embedding of the discrete cube into a Banach space of type 2 would have distortion at least square root n, which is huge. That's a huge distortion because n is the dimension. As you think of a high dimensional situation, the distortion is becoming worse and worse in high dimension. So you see such inequalities, right, they have very strong consequences for the ability to embed something like the discrete cube, a metric space like the discrete cube in Banach spaces, right? If you have a Banach space that behaves in some sense like a Hilbert space, like a space of type 2, that means that the discrete cube cannot be fit in there. It cannot recover the distances like are in the discrete cube, right? So this gives you a kind of example of the questions that Enflo, and he had various other questions along these lines, right? And again, you see this is a linear. I'm allowed to take an arbitrary nonlinear map as my embedding, and still, even if I take a nonlinear map, I cannot reproduce the distances on the discrete cube by putting them in a space of type. So these questions these questions were raised by Enflo, and Pisier, you know, when he realized that you had this Gaussian theorem, right, he thought, well, this must be the right explanation. Maybe there's such a theorem on the discrete cube, and if you were to have such a theorem on the discrete cube, then this conjecture of Enflo would basically be solved. Okay? So Pisier conjectured that the same inequality should hold on the discrete cube, right? So now, let's take epsilon 1 to epsilon n, epsilon 1 prime to epsilon n prime to be random signs, right? And now we take a function from the random signs to a norm space. Well, you know, the natural conjecture is that you can just replace everywhere here the Gaussians by random signs, right? I mean, such an inequality is true for Gaussians. Why shouldn't it be true for the discrete cube? Right? So this was the actual motivation for Pisier to study this question. And he naturally conjectured this. And of course, if such an inequality were true, then that statement over there would follow immediately and the conjecture would be solved. Right? But the proof for the Gaussian case relied completely on rotation invariance. Of course, the discrete cube is not invariant on the rotation. Vectors of random signs are not invariant on the rotation. Right? So the method of proof doesn't go through. And in his notes, he was trying to somehow adapt this method of proof, try to create some random rotation and try to fix some things, you know, so it might work. But he was not able to prove such an inequality. Right? So the conjecture is that this would hold with a universal constant, right? But Pisier was only able to prove such an inequality on the discrete cube where this constant was of order log n, where n is the dimension. So he could get such an inequality, but the constant grows as the dimension grows. Right? And as soon as the constant here grows, this is no longer capturing the kind of phenomenon one expects, right? Because this is no longer a dimension-free constant. C to the p. So somehow or other he was not able to get down to a dimension-free constant, but he conjectured it would be possible maybe with a different method of proof. And unfortunately, in 1993, Talleyrand showed that it's impossible. So Talleyrand just cooked up an example of some norm space and some function for which the smallest possible constant here is log n. And so actually what Pisier managed to prove was already the best possible thing. So, you know, you have this Gaussian principle which is very powerful. You dream of one on the discrete cube. But it turns out that the same inequality in the discrete cube is just false. Such an inequality cannot exist with a dimension-free constant over here. And therefore, it's really a different situation. Which is kind of surprising, because in classical concentration of measure, it's not a theorem, but it's typically the case that things one proves you know, for the Gaussian measure have analogs of some kind on the discrete cube. Right? Maybe with some extra conditions, right? But here, it seems that the best possible constant is log. Good. So now what? Okay, so there followed many years where people were trying to improve this situation, right? So for example, for Enflo's conjecture, you don't really need this general theorem, right? You only need the consequences of it for spaces of type 2. Right? But you know, the counterexample to this inequality where it doesn't hold, where you need the log n, was not for a space of type 2. It was for L infinity, which doesn't have type 2, right? So maybe you could conjecture that for the discrete cube, such inequalities are still true, but they're not true for general norms. They're only true for norms of type 2 or for some non-trivial type, right? And there was a long, even that was not proved. There was a long series of articles, starting maybe with the work of Naor and Shechtman, where they tried to look at special classes of norm spaces in which maybe such an inequality would hold with a smaller constant. Now, they were able to prove such inequalities for so-called UMD spaces. Let me not get into what these are. You know, even spaces, you know, none of these results were good enough to actually settle the original conjecture, because even for finite type, it was not clear. So 2 years ago or so, something like this, we've completely settled this problem. And one of the surprises of the solution is that people were looking for the solution of this problem in the wrong place, okay? Because what everybody was looking at were conditions on the norm for which such an inequality is true, right? This is the obvious analog of the Gaussian inequality, but it doesn't hold for any norm, but maybe it holds for certain kinds of norms, right? That's the wrong solution, okay? It turns out that there is a completely general, exact analog of Pisier's Gaussian inequality on the discrete cube. This is not the right inequality. So let me write down for you the right inequality, or at least some version of it. So this is with Paata Ivanisvili and Sasha Volberg. So it turns out that one has such an inequality, amazingly, with the same constant as in Pisier's inequality. It's an exact analog of Pisier's inequality. In fact, Pisier's inequality is going to be a special case of this theorem. Okay, so I just did everything to the 1 over p just to make it look good. Okay, so the Gaussian inequality says that this is true with a Gaussian here and an independent Gaussian here. We know it cannot be true with random signs here and random signs there. Okay, so it turns out that such an inequality is true. And of course, here you're always putting in random signs. The question is about random signs. So I'm not allowed to change these random signs. And I'm not allowed to change these random signs because the function should be a function on random signs. But it turns out I'm allowed to change these guys. Okay. So it turns out that such an inequality is true, but I should not take here random signs, but I should take here something else. Some other random variables. So these random variables are independent of these random signs, but they're not themselves random signs. They're biased random signs. Okay, so let me write this. So let me define some random variables CIT that are plus or minus 1 with probability 1 plus or minus e to the minus t. So you see they have some bias. These are like biased random signs, right? They are positive or negative with different probabilities. And these delta ITs are just those biased random signs, which I have rescaled to have mean 0 and variance 1, just like the regular random signs. So I've just standardized them. Now they have mean 0 and variance 1, but they're based on these biased random signs, right? So I've introduced some bias here, and I've replaced the linear combination here by biased random signs. Right? And of course, the question is, what should be the bias? There's some t here, right? So in fact, what you can do is you can just average this over the bias. The question is, yes, these random variables are independent of the epsilon i's, right? Otherwise, they're not, and they're independent of each other. The delta ITs they're independent of each other, right? So you have to average this mu dt as some measure on the positive real line, right? On the positive reals, some probability measure. There's an explicit formula for it. It doesn't matter what it is, right, for the application. So you replace these by biased random signs and you average over the bias parameter. And suddenly this inequality is true unconditionally. Okay. This inequality is true for any function on any norm space. And this is the correct analog of Pisier's inequality in the discrete cube. But you see, it's not the average, right? Normally, when we take an analog of a function of the Gaussian case on the discrete cube, we just replace Gaussians by random signs and we're good. But that's not the correct analog of Pisier's inequality. This is the correct analog of Pisier's inequality. It's in fact so strong that you can recover Pisier's inequality from this inequality by the central limit theorem. Right? Because by the central limit theorem, if I take the average of a bunch of random signs and I standardize them, they'll converge to a Gaussian, right? So I can just take here a function where in each coordinate of the function I put an average of a bunch of random signs and take the limit, right? Then by the central limit theorem, this will converge to the Gaussian case. And then on the right-hand side, if you plug in what happens with the central limit theorem, the t parameter no longer matters because they have all mean 0 and variance 1. So the dependence on the bias vanishes and you just get here a bunch of Gaussians. And so you recover Pisier's inequality as a special case. Right? So this completely non-obvious inequality, I should wrap up, but this completely non-obvious inequality is somehow the correct analog of Pisier's inequality. So now this is still just one distribution, and the natural question here is, do we have some analogs of these types of inequalities for other distributions? And this is really a matter of, this is a sort of a major open problem, right? And I have progress on this, which one can, in certain cases, prove inequalities of this kind for a large class of distributions. So unfortunately, both the Gaussian case and this case rely on some sort of explicit computations. So let me, because I am at the end of the talk, let me not go into the proof right now. But the proof of these inequalities is based on the heat semi-group on the underlying object that you're looking at. So there you can write down a completely general inequality in almost any situation, where instead of these delta ITs, what you have over here is the derivatives of the logarithm of the heat kernel on whatever space you're working on. If you look at the Gaussian distribution, you have the Ornstein-Luke process, the heat kernel, you compute the gradient of the logarithm of the heat kernel, you just get here a bunch of independent Gaussians and you recover Pisier. If you take the heat equation on the discrete cube and you compute the gradient of the logarithm of the heat kernel, you find exactly these delta ITs. Right? But if you're in a general space, then you have problems, because if you're in a general space, the gradient of the logarithm of the heat kernel is no longer independent of the variable here, which would make it kind of useless for computations. And the coordinates are no longer independent of each other. Right? So you can write down such a general inequality, but it's useless because you understand nothing about the joint distribution of these two vectors. But it turns out that we have techniques now to understand the distribution of the gradient of the logarithm of the heat kernel in situations, for example, of positive curvature, that allow one to recover useful inequalities by applying comparison principles with respect to the distribution of the gradient of the log of the heat kernel. And this is allowing us to make progress and prove new theorems, but it's still a question whether one can obtain these things at a complete level of generality. So let me end here. Thank you.
Any questions for? Yeah. What exactly does mu depend upon in your inequality?
The question is this mu?
Yes.
This is just some explicit measure. It's the measure with mu dt is the measure with density 2 over pi times 1 over square root e to the 2t minus 1 dt. So you see at near t0, this has a singularity 1 over square root t, which is integrable. Near infinity, it is e to the minus t. So it's integrable. And the integrable of this function is an arc sine or arc tangent or something like this. So this 2 over pi makes it exactly a probability measure. Okay? So it is something that doesn't depend on anything. It's just some formula. It gives you no insight. I mean, I could write down this formula. It gives you no insight into the behavior of this inequality. So I just hid it. Right? But it doesn't depend on anything. Yes?
Why are you defining f on the discrete?
I beg your pardon?
Why are you defining f on the discrete? Why is it not possible to define it on the infinite space Rn and do the ask the same kind of questions?
So the question is, why am I defining f on the discrete cube? But you still want to plug random signs into it?
Yeah, so epsilon 1 up to epsilon n are permanently IID.
Mm-hmm.
And f is defined on Rn.
Okay.
And is this equality true if you don't get differences with this value? Are you able to?
Okay, the question is, why don't I define f on Rn? Right? But then I can still plug in random signs, right? Because random signs take values plus or minus 1, right? These live in real line, right? So I can still plug in random signs. Well, nothing is stopping you from doing this, but you want now to have here continuous derivatives, right? The thing is, you see, I mean, when I plug in random signs, the value of this random variable depends only on the value when you plug in random signs, on plus or minus 1 to the n, right? But the derivative of a function, the calculus derivative of the function, depends on the values of the function near, right, close to the points, right? So there are, of course, many functions f on Rn that when you restrict them to the discrete cube are the same function, but they have completely different derivatives, right? So you cannot expect, right, you cannot expect to see that information, right? If your functions only live on the, if the variables you plug in only live on the discrete cube, you cannot hope to see the derivatives of the function, right? Because derivatives of the function are not determined by their values on the discrete cube, right? So when one has these kind of questions on the discrete cube, it's unnatural to work with calculus derivatives. Such inequalities cannot be true because you can make it whatever you want, right? You can make the derivatives 0, right? I mean, you could take a function on plus minus 1 to the n and extend it to Rn in such a way that the derivative of every point is 0. And then, you know, such an inequality cannot be true.
I was wondering, in the first Gaussian pointer inequality, so can you replace the Gaussian random variables with other random variables, other distributions?
So, you know, the question is, in the Gaussian Poincare inequality, can you replace the Gaussian random variables by other distributions, right? So I wrote down under it that there's huge numbers of extensions of such inequalities to many different settings. But if you ask, for example, if you're asking, for example, about independent random variables, right, because these things even hold for dependent situations, right? But if you're asking about independent random variables, then the answer is yes. And there's a general inequality which was mentioned here called the Efronstein Inequality. Some people call it the Efronstein Inequality. I call it tensorization of variance, but okay. So, which holds for arbitrary product measures. So it says that if x1 to xn are, let's say, independent, they don't have to be IID, any independent random variables, right? And if you take some independent copies of them, so these are just independent copies of these random variables, then the variance of f of x1 to xn, right? So you can bound it, for example, by the expectation of f of x1 to xn minus f where you replace the ith coordinate by its independent copy. Right, so maybe with a factor 2 or 4, I don't remember, right? But here what you do is the derivative, what is the right notion of derivative in this case? Right, for random signs, I just flipped the sign of the ith coordinate. But here what I did is I replaced the ith coordinate by an independent draw from the same distribution. That's also a kind of derivative, right? So this is a completely general inequality that holds for any product measures. And this is called Efronstein inequality. And it is exceedingly useful, okay? It is used heavily in statistics, in combinatorics, and you know, all sorts of different areas of probability. Right? And there are analogs of this inequality also for tail bounds and things like this. But let me just say about this inequality, for this particular situation, I do have a complete generalized vector value, I do have a vector value concentration inequality in complete generality. So there is actually a completely, it's not written anywhere, but there's a completely general vector valued concentration inequality for product measures of exactly the same kind. But you don't have to prove anything new. You can just deduce such an inequality from the inequality for random signs by some sort of symmetrization argument. So there's some cheap trick, you know. There's some cheap trick that once you have an inequality for random signs, you can just upgrade it to a random to such sort of inequalities for general random variables. So these kind of inequalities don't really contain anything new, morally speaking, over the case of random signs. But there are other situations. For example, if you're on a finite graph, right, and you take the uniform distribution over the vertices, and the derivatives are now the difference between the function at a vertex and its neighboring vertices, right? Now, in this situation, this is a kind of a dependent situation, right? You don't have independence. And these kind of questions really do not follow from the discrete cube, right? And, you know, if I were to state, for example, an open question that we know almost nothing about at the moment is which kind of graphs do vector value concentration inequalities hold with dimension-free constants, right? What kind of assumption do you have to impose on a finite graph in order to do that, right? And this is a very interesting question because you see, if you were to have such an inequality, right, then you would immediately get an analog of, for example, Enflo's example, which said that if you have such an inequality, then that graph would not be able, you know, any embedding of that graph into a space of type 2 would have to have distortion at least, whatever, the square root of the degree of the graph or something of this kind, right? So anytime you can prove such an inequality, it gives you very strong constraints on the embeddability of those graphs in other known spaces, right? So it's a very interesting question to try to understand geometrically what kind of geometry can you impose on the graph in order to have such an inequality. And at the moment, this is so for manifolds, for example, I understand this now very well, but for graphs, for graphs, this is really open. And potentially don't know that you know it, which is the Isoparametric Theorem. So what does it say, right? If I look at all bodies with the same volume, right? So I could take a square or a cube, a ball, an octagon, whatever you want. I'd look at all bodies with the same volume, right? Which one has the smallest surface area? Right? We all know this. What is it? It's a sphere or a ball. Yeah, the sphere is the surface, so the ball has the smallest surface area, right? So this is a talk about convex bodies. So this talk is only going to be about convex bodies, and this is indeed the first case that was proved. But you know, of course, this theorem holds more generally among convex bodies with fixed volume, right? The surface area is minimized by the Euclidean ball. And throughout this talk, I'm always going to call the Euclidean ball B, okay, for ball, B for ball. Right? So we all know this, of course, because we've all blown soap bubbles when we were young children, right? And you know, inside a soap bubble, there's a certain fixed amount of air that's trapped. And you know, to first approximation, the air is incompressible, right? So the volume of air inside the soap bubble is fixed. But of course, the surface of the soap bubble can move around, right? But the soap molecules in the surface, they're a film, right? And the surface tension is causing them to want to minimize the surface area, and that's why soap bubbles tend to be round, right? So in principle, this is a very natural theorem that we all know. But you know, what is so special about surface area, right? So what happens if we also fix some other parameters? Right? Why don't we just fix surface area, right? Or sorry, why do we just fix volume, right? We fix the volume, we minimize surface area. Why just fix the volume? Volume and surface area are just two examples of geometric parameters associated to shapes, right? So, you know, we may also fix other parameters, and then, you know, we get interesting problems, right? So the earliest example of such a question, and I'll tell a little bit about the history in a moment, is about the mean width. Okay, so what is the mean width? Let me draw some convex body. Here is some convex body K, here in R2, but you can do it in any dimension, of course. So let's say you draw a convex body in R2, right? Here it is. So if you have to fix a direction. So for example, say I fix this direction, then what I can do is I can look at the width of the body in that direction. So I have to draw two planes with that normal direction. And then this is the width in that direction. Right, so if I want to measure the width of something, I can use calipers, right? I take this bottle, I want to measure the width in this direction, right? So I take two planes that are like this, right? And I measure how far apart they are. Does it make sense? So now if I average the width over all directions, I get the mean width, right? This is a perfectly respectable geometric parameter, right? Just as respectable as volume and surface area. So you could now ask, for example, what happens if I take a body, but I fix the volume? Let's say I fix the volume to be 1. But I also fix the mean width. I say the mean width is, 5, right? And now among all bodies with volume 1 and mean width 5, which one minimizes surface area? Right? Well, of course, if the width that I fixed was actually the width of a ball of volume 1, then the minimizer would still be the ball, right? But now if I fix the larger number, let's say that I fix the width that is larger than the width of a ball of volume 1, right? Then the ball can no longer be the minimizer, right? So I fixed the volume 1, but I fixed the larger width than it wants to be. And now I look among all those bodies. So what's the most efficient way of minimizing surface area if I force my body to be wider than a ball of volume, right? So imagine that we lived in some sort of alternative universe, right? Where, in addition to the normal forces of nature, there was some sort of dark force that forced the soap bubbles to be wide, right? then in that universe, what would they look like? This is the question. Anybody have a guess? Ellipses is the guess here. This is always the guess, ellipses, and that doesn't turn out to be the right answer. If ellipses was the right answer, I probably would not be giving this talk, okay? So the answer is rather amazing, and for many reasons. As you see, it's not a recent result. It turns out the most efficient way is the following. Right? So start with a ball. Here's a ball. And take a point outside the ball. And now what you can do is you can form the convex hull of that point with the ball. And what will happen is that you'll put like a little hat on the ball, right? You put the convex hull, so it's like you have a little party hat, right? And you can put another one on if you want, right? You can do this as many times as you want. So here I took another point outside. Here I put another hat on. Okay, let me put on 2 for sake of illustration. So this is a 3-dimensional ball, but I put 2 hats on it. This object is called a cap body. This object over here is called a cap body. So I took a ball and I had spikes. I have spikes sticking out of it in a convex way, right? These points. And it turns out that these objects, this is the most efficient way to create something that is wider than a ball, right? If you try to minimize volume, right? So I fix mean width, I fix volume, and I want to minimize surface area under those 2 constraints. The most efficient way to do it is to take your ball and have spikes sticking out of it. And in fact, you can put as many of these caps on as you want, so I can keep taking more points outside and take the convex hull, as long as the different caps don't overlap with each other. Okay, so I can put as many caps on here as I want, as long as the different caps don't overlap with each other, right? And you could even have a countable number of caps. They don't have to be finite. All of these bodies are called cap bodies, right? And it turns out that all of these objects minimize surface area when you fix volume and min width. Right? So in many ways, this is unexpected, right? First of all, who would guess that such a thing would minimize, right? But secondly, unlike almost all such problems that appear naturally in mathematics, the solutions of this problem are no longer smooth. You see they have these sharp corners over here, right? So the solutions are not smooth. Moreover, the solutions are not unique because there are many different cap bodies with the same volume and the same mean width, right? For example, it turns out that if I move these caps around the surface of the ball, right, then they have the same volume and the same mean width. So it's a highly non-unique, highly non-smooth situation. Okay. So this is rather surprising. We just changed a little bit the classical isoparametric problem, and suddenly we see very unexpected types of objects show up, right, in this story. Now, you see this example is very old. But it seems a little bit like a curiosity, right? You know, why would you care about this particular problem, right? But in fact, this is a bit of a funny example, but this example actually, it hints at a much deeper structure that lies underneath. And in fact, Minkowski in 1903 discovered this example by studying the behavior of convex bodies. And what I want to explain now is where this example comes from and why one asks these kind of questions. Okay, so in my public lecture in Kolkata, I will talk a lot more about the history of this problem and where it comes from. But for now, let me just give the basic ideas. So the most basic fact, maybe that you could view this as the fundamental theorem of convex geometry, is the following. It says that volume is a polynomial of convex bodies. What does it mean? Okay. So if I take a bunch of convex bodies, so K1 to Km are convex bodies in Rn, right? So we're in n dimension. I take any number of convex bodies, and I take some coefficients. Okay. Then what I can do is I can look at the volume of the linear combination of these bodies. And what I mean by this plus notation is really addition, right? So this is the set of all points, lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3, etc., where x1 is in k1, x2 is in k2, x3 is in k3, etc. Does it make sense? So I'm really taking the points in these sets and adding them up, right, in an arbitrary way. So this, I take the volume of a linear combination of convex bodies, and the amazing fact is that the volume of a linear combination of convex bodies is a polynomial, which should not be obvious to you at all. It's a homogeneous polynomial of degree n, the dimension. So it's a sum of I1 to In is 1 to m of the coefficients, lambda I1 to lambda In. And then we get here, right? So these are the monomials, and then I get the coefficients of the polynomial, which depend on the bodies ki1 to kin. Okay, so this is these coefficients are functions of n of the bodies, right? The n bodies corresponding to the indices that appear in the monomial. Does that make sense? So it turns out, for some mysterious reason, that the volume of convex bodies is a polynomial. Right? Now, if you know this, then it's obvious, but if you've never seen it before, it's a bit surprising. So if you just want to think about a simple example, let's think in 2 dimensions. Let's take a square and add to it epsilon times a ball, right? So this is ball, B is a Euclidean ball of radius 1. So if I multiply every point in it by epsilon, it becomes a Euclidean ball of radius epsilon, right? Now what happens when I add it to K, right? What do I have to do is at every point in K, I draw the ball around it, and then I trace the ball around, right? So what I get is the set of all points within distance epsilon of K, right? What does it look like? So of course K is still in it because the Euclidean ball contains 0. So here we have the original K. And then we have to draw all points at distance epsilon, right? So I have to draw all points at distance epsilon from the shape, right? So here we get a straight line, here we get a straight line, here we get a straight line, here we get a straight line. And then here we get some round bits, right? Right, so this is K plus epsilon B, right? So what is the volume? Well, the original K still sits inside, right? So it's a volume of K. That's this original K. And then I have these 4 rectangles over here, right? So this rectangle, for example, is epsilon, has volume epsilon times the length of this edge, right? And then here I get epsilon times the length of this edge, right? So the next term is epsilon times the sum of the lengths. Right? Well, the sum of the lengths of a square is exactly the surface area of the square. The sum of the lengths of the edges, this is the length of the boundary. That's exactly the surface area of the square. And what is left? Well, there are these 4 pi wedges over here in the corner, right? But each of these is exactly a quarter of the original ball, right? So when I add the volumes of these 4 corners, I get exactly the volume of epsilon times a ball, which, because we're in the plane, is epsilon squared times the volume of a ball. Right? So you see in dimension 2, the volume of K plus epsilon B is a polynomial of degree 2 in the coefficient. Not just that, but these coefficients that we get in the polynomial have a very natural geometric interpretation. They're not just some weird things. Right? They're actually volume and surface area of the 2 bodies that we get. Does that make sense? So it turns out that this, right, Minkowski's theorem says that this picture over here holds in complete generality. If you view volume as a function of convex bodies, it's a polynomial. In dimension n, it's a polynomial of degree n. And its coefficients over here, they have a name. They're called mixed volumes. And these mixed volumes, these coefficients of the volume polynomial, can be viewed as a very, very large family. These are, in some sense, the most natural geometric parameters associated to convex bodies. And many, if not almost all of the type of geometric parameters people typically study for convex bodies are just special cases of these coefficients of the volume polynomial. Okay, so if we take another example, right, in R3, right, so in R3, so the volume of a convex body with itself 3 times, the mixed volume is just a volume. This is easy to see from the definition. If I replace one of the guys by a ball, this is some constant, probably 3, times the surface area. So exactly like in this example, the coefficient of the linear part of this polynomial is exactly the surface area. But for example, if I replace two of them by a ball, up to again some universal constant, you can compute these, I just don't remember them. This is exactly the mean width of K. And now you see how you arrive at that strange example over there, right? Because for three-dimensional convex bodies, volume, surface area, and mean width are exactly the three natural geometric parameters associated to a convex body K if you're interested in Euclidean geometry, right? Where you place some of them by Euclidean balls. So these are the three natural questions to ask about the geometry of three-dimensional bodies, because these are exactly the coefficients that show up in the three-dimensional analog of this example over here, right? But in general, in n dimensions, and even in 3 dimensions, I could take 3 different bodies, and these would have geometric interpretation. In n dimension, I can take the mixed volume as a function of n convex bodies. I can take n bodies, and they encode a huge amount of geometric information. So before I move on, let me just, basic properties, I'm just going to take them for granted. So the mixed volume is, first of all, symmetric in its arguments. That means that the mixed volume of n bodies doesn't depend on the order in which I take the bodies, okay? Symmetric if I permute the order. This is more or less by construction, right? Because these monomials, of course, don't depend on the order. So there's no, right, I mean, you just define them to be symmetric. Right? They're additive, or they're multilinear, let's say. Right, so if I replace K1, right, by AK plus BL, then the mixed volume will behave exactly linearly, right? This is the A times the mixed volume of K, blah, 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 plus B times the mixed volume of L, blah, 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 right? So it's linear, let's say, in each of the coordinates. This is, again, more or less by definition. Okay? That follows because they're the coefficients of the volume polynomial. The more important one is that they're non-negative, and this is not an obvious fact. It requires proof. It turns out that not just is the volume of convex bodies a polynomial, but the coefficients are all non-negative of this polynomial. It's a polynomial of non-negative coefficients. And so these mixed volumes, you should really view them as a kind of geometric quantity. And this can be understood in a very general situation. Okay. So once you understand this basic fact about convex bodies, then it's natural to expect that, you know, if you want to do geometry, right, if you want to say something about the geometry of convex bodies, then you should try to find relationships between the coefficients of the volume polynomial. And Minkowski realized that there are extremely general set of inequalities satisfied by the volume polynomial in dimension 3. And nowadays we understand that they're much more general, they hold in any dimension n, and in this setting, this is called the Alexander-Fenchel inequality. So, but in dimension 3, the Alexander-Fenchel inequality was proved by Minkowski. Okay, so this dates back to Minkowski's original paper in 1903. And it says the following. If I take the mixed volume, so I'm now in Rn, so the mixed volumes are functions of n bodies. So let's take KL C1 to Cn minus 2 squared is greater or equal VKK C1 to Cn minus 2 times VLL C1 to Cn minus 2. It's a kind of quadratic relationship between these polynomials that you get from volume have a huge set of inequality because their coefficients form these kind of quadratic relationships with each other. And in many ways, this is the fundamental theorem of convex geometry. A huge number of geometric inequalities that were proved before or after are really just special cases of this inequality or follow from it by iteration. Okay? So it turns out that this very general inequality sort of unifies a very large class of the kind of geometric inequalities that hold for convex bodies. And the question is, what is the difference between the KL and the CIs? They're all convex bodies. But if you, and this is important, will be important later, if you look in this inequality, the CIs and the KL play a different role. because the CI's are the same in all three terms. And what varies are the K and L. Okay. Right, so this is, right, so you have the same C's both sides, I'll call those the reference bodies, and you vary, here you have KL, here you have KK, and here you have LL, right? So you see this looks a lot, if you fix C1 to Cn minus 2, and you just view this mixed volume as a function of two of them, it's just like a quadratic function of two convex bodies. And then this looks exactly like the Cauchy-Schwarz inequality, except the Cauchy-Schwarz inequality would have the inequality sign going the other way, right? So this is exactly the Cauchy-Schwarz inequality for mixed volumes, except that the inequality goes the wrong way. And this is a very fundamental idea that I'm not going to talk about today, but that is very fundamental to the interpretation of this inequality. Okay? So, but you should think about it that way. But if you wanted to vary more of the bodies, you could iterate this. You could apply it several times and combine those inequalities, and then you get inequalities where you vary more bodies. But this turns out to be the basic case that is explaining everything else. But that's not obvious, that shouldn't be obvious that that is true. Thank you. Yes, a convex body is a compact convex set. Okay. Because we're talking about volumes, it doesn't make sense to talk about non-compact sets. They would have infinite volume. Good. So this is in many ways the fundamental inequality, the fundamental theorem of convex geometry. And so it was Alexander von Fenchel. So the history of this is that Minkowski proved this. Minkowski's name should really be added and Fenchel's name should be deleted. Okay, so Minkowski proved this inequality in dimension 3 in 1903 in the same paper that I was talking about earlier. And his proof extends to dimension n if all of these bodies are the same, C, 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 C. But his proof fails if you take different bodies here. And it was long conjectured, some other special cases were known before, it was long conjectured that this completely general inequality should be true in dimension n. And at some point around 1936, Fenchel published a note in the Compte Rendu saying that he had proved it without a proof. Okay? And then at the end of it, he said, here is a sketch of the proof, and then he writes something that makes no sense whatsoever. Okay? And like the next year, in 1937, Alexandrov published a proof. He doesn't cite Fenchel, apparently unaware. You know, between Russia and France or Germany, wherever Fenchel was you know, not necessarily good communication. Alexandrov published a proof, completely correct proof of this inequality in 1937. Fenchel never published a proof of this inequality. He only published this note where he said he had proved it. He gave some sort of hint of the proof, which nobody has been able to understand. I tried myself to read it. I have no idea what he's talking about. Okay, so it is somewhat doubtful that he actually had a correct proof, but it is still called the Alexandrov-Fenchel inequality. It was proved by Fenchel in so let's say 1937. But Minkowski proved in 1903 the three-dimensional case. And the basic question here, which already Minkowski asks, and Alexandrov, so this question has been around since the very beginning of this theory, is for which KL C1 to Cn minus 2 do you get equality? But here you have an inequality, holds for arbitrary convex bodies. So is this inequality sharp? Well, obviously it's sharp, because if I take K equals L, then I have the same on both sides. Well, that's an equality case, right? The question is, are there any other cases of equality? Good? This question has been around since the very beginning of this theory, since 1903, let's say in some form or another, and in complete generality, this question remains open to this day. But let me explain what this question means. Maybe, let me keep this up for a moment. So let's consider one special case of this example. Suppose we're in dimension 3, okay? So, and I'm going to take, let's say, L and C. So now I'm in dimension 3, so I have K, L, and C, C1, just C1. I'm going to take C and L to be Euclidean balls, okay? Or maybe I'll take, let's see, I'll take C to be K and L to be Euclidean balls. So what is the inequality I get? I get V, B, K, K. B is a Euclidean ball, K is any convex body, Now, what does it say? We can replace this by BB or KK, right? So this is greater or equal than VB, BK, V, K, K, K. Okay. That's one case of this inequality. Now remember, I already talked about this example, right? This object over here is proportional to the surface area of K. This object over here is proportional to the mean width of K. And this object over here is the volume of K. So here we have an inequality that relates surface area, mean width, and volume, right? So what happens if we look at all convex bodies with volume 1 and mean width 5, right? Well, if we do that, then we fix the right-hand side of this inequality, right? It's 5, or whatever, up to some constant, right? So if we fix mean width and volume, then we fix the right-hand side of this inequality, right? So this inequality that says that any convex body K with those constraints has surface area greater or equal than that number, right? So if we can identify a convex body for which it becomes equality, then that equality case exactly minimizes surface area among all bodies with the same volume and the mean width, right? And therefore the solution of the isoparametric problem for mean width and volume is exactly given by the equality cases of this inequality, right? Now we know there is at least one equality case. What is it? It's when K is equal to B. Because when K is a Euclidean ball, we have here BB, 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 you have equality. So certainly the ball satisfies equality, right? So of course, if you fix mean width, it might not be the mean width of the ball of that volume, right? But certainly the ball minimizes surface area if I fix the product of the volume and the mean width, right? But if I choose a different mean width, maybe there are no equality cases, right? It's not clear, right? But it turns out that the equality cases are exactly cap bodies. So when K is a cap body. So it's not just the ball that's an equality case. When K is a cap body, then you always have equality in this inequality. And that explains exactly the example I gave here in the beginning, right? That's just one special case of the problem of settling the equality cases of the Alexander-French inequality, right? It explains the solution of the strange isoparametric problem. And in Minkowski's original paper in 1903, he realized that cap bodies are the equality cases, of this inequality. And he in Minkowski's paper, he claims that those are the only equality cases, but again, there's no proof. And nobody's ever found the proof in any of Minkowski's papers. And it was proved 40 years later by Bohl that this is indeed true, right? So indeed, the cap bodies are the only equality cases of this particular case of the Alexander-French inequality. So that's the connection with the example I gave in the beginning. You see, it's a natural question that arises when you start studying the general theory of volumes of convex bodies. But of course, when you have the general Alexander-French inequality, you could view this as a vast generalization of the isoparametric theorem to many other situations. And there are many other kinds of isoparametric type theorems you could write down. And the question is, what are the extremals of these isoparametric theorems, right? So in general, right? So if the equality cases of the Alexander-French inequality, right? They are basically in one-to-one correspondence with extremal problems in convex geometry. Right? Understanding the equality cases of the Alexander-French inequality is more or less equivalent to understanding these kind of questions of if I fix two mixed volumes, which one minimizes the third mixed volume? And these kind of questions in complete generality remain open. So that was first, right, they were first studied by Minkowski, but if you read the paper of Alexander, for example, he states this question explicitly, okay? And it's not at all clear what it is. Even these cap bodies, where do they come from? Why cap bodies, right? What is going on? It's completely unclear, right? And actually the proof of Bohl that cap bodies are the only equality cases is very uninsightful and doesn't actually extend to any other situation. It doesn't really explain a lot about what's going on. So, good. Are there any questions? All right. So this question is very old, and there was almost no progress for maybe 80, for 80 years or something like that. And very recently, in the last 2 years or so, we managed to settle perhaps the most important cases of this problem, and that's what I want to talk about. But in fact, before I do that, I want to switch gears and talk about something completely different. Okay? So, you know, you can ask these questions in convex geometry. I hope that you are convinced that these are interesting questions, right? You have these sort of strange isoparametric problems. But it turns out that these type of questions show up in all sorts of unexpected places. And I want to give you just some sort of idea of it. Okay? So let's completely change gears for a moment. Okay? And let's talk about combinatorics. So if I take a sequence of integers, let's say non-negative integers, right? Non-negative integers. So such a sequence is called log concave. If it satisfies the inequalities ni squared is greater or equal than ni plus 1 times ni minus 1 for all I. Usually we start at 0. It doesn't matter how you index them, of course. Okay? So a sequence of integers is called log concave if it satisfies these kind of inequalities. The reason it's called log concave is because if you take the log of this, if we call, let's say, ki the log of ni, this just says that ki is greater or equal than the average of ki plus 1 and ki minus 1, right? If you take the log. So the log of this is concave in sort of the obvious discrete sense. Okay? And log concave sequences are very natural objects. For example, all log concave sequences that are not 0 are unimodal. They first increase and then decrease. That's not hard to prove, right? So this is a kind of strengthening of unimodal sequences. Right? And it turns out that, for example, in combinatorics, it turns out that there's a huge number of combinatorial problems where you have certain things that you can count, right? Combinatorics is about counting, right? Where you can, when you count certain kinds of objects, that they give rise to sequences that are log concave, okay? And this is a phenomenon that's been observed for a long time, right? The most simple example is if you take ni equals n choose I. This is a combinatorial object, the number of ways that I can choose I things out of n items, right? This forms a sequence. This sequence is log concave. You can check it by hand. There's nothing deep about it, right? But this is a rather, silly example. But it turns out that in many non-trivial combinatorial problems where you can define such objects, it just so happens that they're log concave. And it's been a long-standing question to try to explain why are so many sequences in combinatorics log concave? And in fact, in very recent years, there were major problems of this kind that were settled by June Har, my colleague at Princeton, who just got a Fields Medal for this work. Okay, so these are very natural kind of questions to ask in combinatorics to explain this kind of behavior. Now, one of the first examples of this phenomenon was due to Stanley, and Stanley was studying. He studied various questions like this, but so suppose that I start with some partially ordered set. So I have a set alpha. It contains n elements. I'll call them x, y1 to yn minus 1. So I distinguish some element x, doesn't matter which one. So it's a set of n elements, and on it is some partial order, right? So it's not a total order, it's a partial order, right? Some pairs are ordered, other pairs are not really. So I start with a partial ordered set. Now, if I take any partial order on a partial ordered set, I can always extend it to a total ordering. Okay, so I can always find a total order on a set that agrees with the partial order. It's very easy to do this, right? For example, you could, if you want to define such a total order, first take all of the minimal elements with respect to the partial order, just put them at the beginning of the total order, remove them from the set, then take the next minimal elements, prove them at the beginning, right? Remove them, etc. Right? You could just, by a greedy way, you can extend any partial order to a total order. But the question, of course, if you're a combinatorialist, is in how many possible ways can you do this? Right? So Stanley defined the following numbers. So ni is the number. So you fix up any partially ordered set, right? And now you try to count the number of linear extensions of alpha such that this distinguished element X has rank I. Right? So in how many ways can I extend this partial order to a total order, such that in the total order, the number X is the ith smallest element? Is the question clear? Right? Linear extensions. So this is the number of ways that I can take this partial order and turn it into a total order. That's called a linear extension, right? So because this is not a linear ordering, because it's a linear ordering is a total order, right? So a linear extension is an extension of a partial order to a total order, right? And then we want to know in how many ways can we do this so that the element X gets rank I, right? So as I change I change the position of X in the total ordering, right? And you can wonder in which way does the number of linear extensions change as I change the position of some distinguished element. Is that clear? So this is a non-trivial combinatorial problem. And there's no reason to expect, any nice behavior of these numbers. Why should this behave nicely as I change the rank of the element X, right? But it was conjectured, I'm not sure, but I think mostly based on experimental evidence, it was conjectured in the 1970s by Rivest, by combinatorialists, that this sequence is unimodal. That at first, as I increase the rank of X, right, the location of X in the total ordering, then first I get more and more and more linear extensions, and then eventually I get less and less and less linear extensions, right? But it's not obvious why that should be true. And combinatorialists, how they prove things, they try to perform some sort of injections between different sets, right? And, or bijections and things like this. So they tried to do this, and they were able to prove this for certain, very special kinds of partial ordered sets with, for example, only 2 chains in them or something like this. But, in general, this was completely unclear. So Stanley proved, in fact, in the 80s, Stanley proved that this sequence is log concave. And therefore, it's in fact unimodal. It's even stronger than unimodal. It's in fact a log concave sequence. How did he prove it? Well, so what Stanley did is you give any partially ordered set as input. What he did is he constructed 2 convex bodies, K and L. So this is a subset of, let's say, Z in 0, 1 to the n minus 1, okay? And this is the set of all sequences of numbers between 0 and 1 that agree with the order, with the partial order, right? So that Zi is less or equal Zj if Yi is less than Yj, right? So each coordinate of this vector corresponds to one of the Y elements of the post set, right? And if in the partial order one element is less than another, then the corresponding numbers here are less than. This is called an order polytope. To any partial order is associated an order polytope. So L is the same way, but so this is called the order polytope, but we have an extra condition. So K would have that Zi is 1 if Yi is greater than X, and this one would have Zi is 0 if Yi is less than X. Okay, so there are 2 such polytopes. Doesn't matter for our purposes exactly what they are, but they're convex bodies, right? So they're convex bodies that are somehow constructed from this partial order. Right? And what he realized, which, it's a proof basically obtained by some geometric argument, that these numbers Ni, which are purely combinatorial, right, actually turn out to be the mixed volumes of these 2 convex bodies. So we're in dimension n minus 1. Right? We're in dimension n minus 1, so we plug n minus 1 bodies in here. So we do k some number of times and l some number of times. So we do these I times, and then we do here these n minus 1 minus I times. Either this way or I've changed k and l. I can never quite remember, but something like this. Right? So it turns out that we can take these combinatorial objects and represent them in terms of mixed volumes of certain kinds of polytopes. And to prove this identity, you basically have to take these polytopes and dissect them into simplices. And each simplex turns out to correspond to one of the linear extensions that you have over here, and then everything works out well. So this is a kind of manual argument. Right? And once you have this, then, the rest is obvious by the Alexander-Fenchel inequality. Right? Because what does the Alexander-Fenchel inequality say? It says that the square of this thing, so we take the k and L to be k and L, and the remaining k's and L's are the C1 to Cn minus 2, right? So the Alexander-Fenchel inequality says that the square of this is greater or equal than this thing where we replace one k by an L, and times this thing where we replace one L by a k, right? So if I replace one k by an L, then I get ni plus 1, ni minus 1. If I replace one L by a k, I get ni minus 1, right? And so this inequality is just nothing else than Alexander-Fenchel inequality, right? That's the proof. Now, it's a bizarre proof. You have a completely combinatorial question, and the only known proof of this, at least now there is one other proof, but it's not really, it's okay. I can tell about it later, but really the only known general proof, at least at this time, was completely geometric. Did not involve combinatorics at all. Right? But so this is a rather surprising aspect of this issue, that the Alexander-Fenchel inequality seems to explain the lock concavity of this particular combinatorial problem. Okay? And the way that I think you should really think about this question is that this thing is really a kind of isoparametric inequality for partially ordered sets, or at least for pole set extension. Right? This thing is just the Alexander-Fenchel inequality applied to some particular convex bodies K and L. So this is just some sort of isoparametric inequality, like the one that we had for mean width, volume, and surface area, right? Except here, the mean width, volume, and surface area are linear extensions numbers with different ranks. But geometrically, this is exactly the same phenomenon that's going in. So here we have a kind of isoparametric inequality in a combinatorial setting, right? And once you have an isoparametric inequality, you can ask the associated problem of extremal combinatorics, right? Which is which partially ordered sets, if I fix an I, which partially ordered sets minimize the left-hand side under the constraints that we fix the right-hand side. Right? That's the associated extremal problem. Right? And as you see, this reduces in some sense to understanding the same kind of question that Minkowski asked originally, right? About convex bodies. So let's switch back to convex bodies, and I'll tell you what is known now. And I'll try to explain later why you will care about this combinatorial problem. So let's talk about the equality cases of Alexander-Fenchel, right? So let me remind you what the question is. The question is, when do we have, right? So the Alexander-Fenchel inequality says that VKL C1 to Cn minus 2 squared is greater or equal than VKK times VLL, right? Right, so the inequality says this is greater or equal than that, so we want to know when we have equality, right? So for a very long time, this conjecture existed since the very beginning of the theory, but for a very long time there weren't even conjectures, right? The case of cap bodies, which was known much earlier, was a very special case that was studied sort of on its own, right? But for the general case, there wasn't even a conjecture. But in 1985, Schneider published a conjecture about what equality cases should be. And the conjecture is completely non-trivial, and without this conjecture, I don't think any progress would ever have been made. Because, you know, in principle, it was believed, you see it in books, it was written in textbooks in convex geometry, that the equality cases of this inequality are not known. Probably the reason is that there's so many equality cases that there's no meaningful way of understanding them. That's written literally in textbooks from the 70s on convex geometry. But Schneider published a conjecture about what these equality cases should be, which spurred the progress that came after. So let me remind you, you see these things are called reference bodies. they are fixed, right? They're the same in all three terms. So the only thing that varies is K and L, right? So these bodies in K and L play a different role in this inequality, and they should play a different role in the characterization of the equality case. So I'm going to be a little bit vague about the definitions. I just want to give you an impression of what's going on. Okay. So the bodies C1 to Cn minus 2, they define a set of directions in the unit sphere, okay, that are called C1 to Cn minus 2 extreme. So given any convex body C1 to Cn minus 2, there are some distinguished directions, maybe uncountably many, maybe finitely many, doesn't, we don't know, right? There's some special directions in the unit sphere that are called extreme for this collection of bodies. So let me not define how these are defined in general, but let me, just to give you an impression, for polytopes, right? So if these C1 to Cn minus 2 are polytopes, right, bodies with a finite number of facets, right, then basically what it means is U is C1 to Cn minus 2 extreme. If and only if the faces of Ci with normal direction U contain linearly independent directions. So you have a convex body, you fix some normal direction U, then there is a unique plane, hyperplane that touches with normal direction U that touches the body. Right? You just take a plane with normal direction U, you move it until it touches the body. There's a unique such plane. It touches the body in a certain set called a face. For polytopes, they have a finite number of faces. So the faces completely determine what's going on, right? So for example, it could touch in a point, that's a face of dimension 0. It could touch in a line, that's a face of dimension 1. It could touch in a face of dimension n minus 1, that's called a facet, right? So a direction is called C1 to Cn minus 2 extreme if I look at the face of C1, the face of C2, etc., with the same normal direction U, that these faces contain enough linearly independent directions, right? That each face I can pick a direction so that those directions are linearly independent. Does that make sense? So don't worry if you didn't exactly catch the meaning of this, right? There are some sort of special directions U, and typically these are, for polytopes, for example, this set of directions that are extreme is always finite. Most directions are not extreme. So for polytopes, there's only a finite number of points in the unit sphere that are extreme, right? But these are the directions in which the behavior of the faces of the body with that normal direction are sufficiently rich somehow. They contain sufficiently much linear independence. Okay? And the conjecture and for general non-polytopes, this definition with the faces doesn't make sense, but there's some sort of analogous definition that's local, okay, rather than global. So Schneider's conjecture was the following. We have equality in the Alexandrov-French inequality if and only if K and some homothet of L. Remember, mixed volumes, they're invariant. Okay, maybe I didn't say it. Mixed volumes are invariant under translation. If I take a body and I just move it, it doesn't change the mixed volume because volumes are translation invariant, right? Similarly, if I rescale a convex body, then the mixed volume will be just multiplied by that scaling factor because they're linear, right? But because I have two mixed volumes on both sides of this inequality, if I rescale the bodies, nothing changes, right? So if I have any equality case KL, then if I translate and scale L, let's say, it's still an equality case. So I have to allow myself this, right? So the obvious equality cases would be when K is equal to AL plus V. Those are always equality cases, right? But Schneider's conjecture was that the correct definition of the equality case is not when K is equal to AL plus V, but only that K is equal to AL plus V when they're viewed in these directions U determined by the remaining bodies. have the same supporting hyperplanes in all C1 to Cn minus 2 extreme directions. So because it's hard to tell anything from such an abstract definition, let's just go back to our example. Say, A is some positive number, and V is some vector in Rn. So I'm just allowing myself to have an arbitrary, to translate and scale L, because this inequality, and therefore the equality cases, they're invariant under translation and scaling. So if I had any equality case KL, then K and AL plus V would be an equality case too for any A and any V. A being a positive number and V being a vector, right? So I just have to allow myself to have this freedom in the, does it make sense? Okay. So let's go back to an example.
One question.
Yes?
So the other geometric inequalities you derive using the Alexandrov feature, those the equality cases were already known, right? Many of them.
Well, for some of them, but most of them not, right? Right? So for example, the cap body inequality, right? The inequality with volume, mean width, and surface area, the cap bodies are the equality. That was really in Minkowski's paper that he realized this. But that was a special case. For other inequalities, okay, so first, the really classical inequalities, yes, often they're trivial, right?
And those will also not follow if this equality case.
Yes, if you know the equality cases of this, then even the cases that are trivial, like the isoparametric inequality, the ball is the only minimizer, right? That's because why? That's because if I pick, for example, all right, if I take, for example, in dimension 3, you only have one body. But if it's a ball, every direction is extreme for the ball. Right? So if you pick C1 to be a ball and you're in dimension 3, so you only have one body, then every direction is extreme, which says that K and AL plus V have to be the same in all directions, which means that they're the same, right? But in that case, L is equal a ball too, right? In the isoparametric inequality, and therefore K must be a ball, up to translation and scaling, right? Good? So in such situation, all directions are extreme and you don't have any problems. Right? So let's remind ourselves what happens in the case of a cap body. So in the case of a cap body, K, right, a cap body we have K, L, and C1, right? We're in dimension 3. Right? So K might be, for example, the Euclidean ball, right? And then L and C are cap bodies. Right? So let's say we add a cap. Okay. So in the case of this inequality, right, you see C and L really play a completely separate role in the general inequality. So in the equality cases, they play a separate role, but you can, of course, choose L to be equal to C. And that's what happens in this. That makes this inequality rather special for cap bodies, right? But let's think about C being a cap body. So what directions are C extreme? Okay. So this, of course, is not a polytope. So the definition I wrote there is not so clear. But nonetheless, right, what you can see here is that, for example, if I have if I look at a direction that is normal to this corner is a face of dimension 0. It doesn't contain any linearly independent direction. It's a point. So any normal direction, right? There is the set of normal directions of this point. These directions are not C extreme, right? But in this case, all other directions, so any direction that's, let's say, normal to a part of the sphere that's not a point, are C extreme in this case. Because locally, even though this is not a polytope, locally it looks like a manifold. So locally it is flat. So locally it looks like a face of full direction, and therefore these are extreme points. Okay? So what does the conjecture of Schneider say? It says that you have equality if K and L agree in all C extreme directions, right? Now obviously K and L are not the same. They don't agree because L has this giant spike sticking out of it, right? But you see, if I fix any direction that's extreme, so every direction that's normal to a point of the ball, well, that's exactly a direction in which you don't see the spike, because those extreme directions are exactly the directions where you don't see the spike, where you see the ball. So in those directions, these two bodies look the same. Now these two bodies, this body has a spike, but to see the spike, you have to look at the, right? If I look at something at the normal direction to this guy, then it's the touching plane here is here, but if I draw the same plane over here, it's somewhere up there, right? So you see, for the ball, the touching plane in the same direction is not in the same place, because there is the spike, right? So the ball and the cap body are different, but they're different only in those places that are normal to the point over here. But those are not extreme directions. And that explains why you have this cap body behavior. So I hope this gives you a better intuition for what is going on. So in general, right, and I can give, let me not do it, but we can give many more examples. Also for polytopes, it's very easy to give examples.
I have a question. So is it obvious that if always you have these extreme directions, I mean, is it possible to arrange polytopes so that you are left with no extreme?
I don't know whether it is obvious, okay? But if your bodies have non-empty interior, which is not necessary for these things to make sense, if your bodies are full dimensional, they're not pancakes, right? Because you can consider, for example, R3, a two-dimensional disk that's sitting in R3 is also a convex body, okay? But it has empty interior, right? So, for example, I could take each of these C's to be just a single point. That's also a convex body, right? Then there are no extreme directions. Okay. But if your bodies are full dimensional, then there's always extreme directions, and it's known exactly when they exist. And but it shouldn't be 100% obvious, but it's also not very hard to prove. But it's a very good question. The conjecture is that if you have equality, so in complete generality, neither direction of this conjecture was originally proved. With some unpublished work that I have with my PhD student that we're still working on, we can prove that direction, okay? But that's the easy direction. But the really interesting direction goes that way, okay? So the statement is that if you have equality, then there exists some A and V such that this is true, right? And the converse direction is for every A and V, if you have this, then you have equality. Okay, so that's the way that you should read this.
Yeah, I had a question.
Yes.
So you have these extreme directions, right?
Yes.
Typically, you should be able to capture convex bodies in some kind of minimal ellipsoids of some sort. So is there any relationship between those?
None whatsoever. No. No. These extreme directions are really talking about the structure of the surface of the convex body. So this is not related to the John ellipsoid, the touching points of the John ellipsoid. This is something completely different. This is something about the structure of the boundaries of these convex bodies, not just of one body, but how the structures of these convex of the boundaries of these n-2 convex bodies interact with each other. Right? So it is a really non-trivial notion. So wow. Okay. So what have we done? So we proved Schneider's conjecture is true. Not quite. First of all, what we did is we assumed that C1 to Cn-2 are polytopes. This is the combinatorial setting. So let's assume the reference bodies are polytopes. Okay. In this case, we prove Schneider's conjecture is true if they are full dimensional. Right? So they have interior points. But otherwise, you can have many more equality cases. which we fully characterize. So in the case where all the reference bodies are polytope, we've completely settled the problem. When the bodies are full-dimensional, Schneider's conjecture is true, and in fact under some slightly weaker assumption than that. But one can construct sets of bodies C1 to Cn minus 2 where some of them are flat, like pancakes, where in fact you have many more equality cases than are conjectured by Schneider, and they're rather complicated. So I am not writing them down because it would take me quite a while to explain what they look like and what they are. They're much more complicated than the Schneider ones, but we've completely understood all of the equality cases in the case when they're polytopes. And what this allows us to do is, if we now go back over here to Stanley's example, then we can similarly, using this characterization, we can characterize for which partially ordered sets you have equality in Stanley's example. Okay? That's not entirely obvious, because when you apply the equality case of Alexander-Fetchel, you get a geometric statement about the polytopes K and L. But for that to be interesting, you have to translate that geometric information back into combinatorial information about the partially ordered sets, and that requires work. So there's extra work to be done on top of the geometric picture. But nonetheless, one can go back and one can really use this to settle this problem of Stanley. And because I'm out of time, what I want to give you an idea of what it tells you, right? Why would you care about solving this isoparametric problem, right? So in principle, all Stanley is telling you is that the sequence of numbers is log concave, right? So it's unimodal, right? And it's log concave. But it doesn't tell you what kind of log concave sequences you can get. You would think maybe any log concave sequence I can cook up a partially ordered set such that you would get this. Right? It turns out not to be true. Once you understand the equality cases, you can understand a huge amount of information about these sequences. Right? So first of all, they're unimodal, so they start at 0 or maybe not at 0. Typically they start at 0, but they may not start at 0, so they can be 0 for a while. Then they can increase, right? Now, in principle, a log concave sequence, right? So you can have some maximum over here, and maybe they will decrease again, and maybe they'll become 0 again, okay? So it doesn't have to look like this. For example, you can end here above 0, you can start above 0. It depends on the situation, right? But let me draw some sort of generic picture like this. So this is a unimodal plot, right? But in principle, for example, you could have a 3-term geometric progression. You could have that ni equals twice ni minus 1 and ni plus 1 equals twice ni, right? But the equality case characterization says that that's not possible. So first of all, if as soon as you're not at the maximum or at the minimum, you have to be strictly log concave. So this is already not obvious, that you cannot have any geometric progressions inside the sequence. Completely not obvious. Right? Secondly, our characterization, you see, so such sequences can only look like this. For some region you're 0, then you're strictly log concave for a while, then you achieve the maximum, then you're strictly log concave going down, and then you are 0 again. Using our characterization, we can compute exactly where these points are. Because each of these points agrees with where you start getting equality cases, right? And we characterize exactly when we have equality cases in terms of the partially ordered sets. So once you have such a characterization, I can give you a formula in terms only of the definition of the partially ordered set. Where is this point? Where is that point? We can compute them. You give me any partially ordered set, I will compute for you what this picture looks like. That's an enormous amount of information. Just knowing your log concave just says something very vague about the shape of these sequences. Once you understand these kind of isoparametric inequalities, suddenly you have a huge amount of information about what these pictures actually look like that you can actually compute for any given partially ordered set. So it gives you some sort of idea that what kind of information you can extract that's completely unexpected from these kind of things. So let me end here. Thank you. Yes.
Elementary question. So the volume of, let's say, we have two convex bodies. The volume of lambda k plus n. If we write it out, so it's like a quadratic equation, right? Like we can these volumes, lambda square.
Only in dimension 2, right? It's an equation of degree of degree n in dimension n.
Yeah. So let's stick with dimension 2 then. So in that case.
So in dimension 2, let me just clarify. In dimension 2, there are no interesting equality. There are only trivial equality cases, because in dimension 2 there is no C. If you're in dimension 2, there is no C. So in dimension 2, every direction is extreme. Okay. So the interesting situations begin in dimension 3. I don't know whether this would change your question, but just to clarify.
Yeah, it was actually much more basic.
Okay.
Because so the volume is always positive.
Yes.
Unless it's zero, unless there is some scaling between like K and L. So in that case, effectively the Alexander potential inequality looks like you're computing some discriminant and saying that it's positive or negative. But somehow when I work it out, it goes the other way.
Yes.
So I'm just wondering, like, maybe I have a computation. That's most likely.
So if you form the 2 by 2 matrix, the 2 by 2 matrix. Of course, this is equal to that by symmetric invariance. Right? And you take the determinant. The Alexander-Fenchel inequality says that other way around. Is that true, or is it negative? Negative. That's negative. This minus that. Yes, it says that it's negative. Right? So the determinant of this 2, but this is another way of writing the Alexander-Fenchel inequality. And you might wonder what happens if you have 3 bodies, K, L, and M. You can also form a 3 by 3 matrix, K, 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 L, K, M, right? Okay, you know what I mean. L, K, L, 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 M, and right, form a 3 by 3 matrix with 3 bodies. Then the determinant will be positive. And if you do it with 4 bodies, the determinant will be negative. Now you can do this with K bodies, and the determinant will have sign the -1 to the K minus 1. Okay? And but it turns out that all of those, you see, so those are inequalities when you have not just 2 bodies, K and L, but you have K bodies that you put in the first 2 slots, right? But all of those inequalities follow from the 2 by 2 case. Now those inequalities are called Shepard's inequalities. So once you understand the 2 by 2 case, there is some linear, I mean, this has nothing to do with convexity. This is a linear algebraic fact that as soon as you have such a situation, you can reduce this to dimension 2. And so you get all sorts of inequalities that you get from this 2 by 2 case, right? But such quadratic forms are called hyperbolic because, right, this is a 2 by 2 matrix whose determinant is negative. So it has 1 positive eigenvalue and 1 negative eigenvalue. And this is a very basic, right? So this is a hyperbolic inequality, and the Alexander-Fenchel inequality is a hyperbolic inequality. And this idea is very fundamental to its proof. So when you prove it, you indeed are trying to prove that when you form a matrix of this kind, you have exactly 1 positive eigenvalue and all the other eigenvalues are negative. And then, you know, that is one of the key ideas behind the proof of the Alexander-Fenchel inequality.
If I multiply, let's say, -1, then each like principal block has determined positive determinant or negative determinant, right? Like if I multiply like all the entries in that matrix n by n matrix, which I get, then the corner entry is negative. The next block has again negative determinant and so on. So what sort of matrices have this property? All the blocks that determine less than equal to 0.
It's not all the blocks, they will alternate. They should alternate.
I'm just saying,
Good.
I'll multiply -1.
May I recommend to you a beautiful book written by your esteemed colleague in Delhi. Where the question you're asking me is explained in great detail. There's an entire chapter answering that question, and as I recall, there is one theorem in this chapter, I don't remember the number of it, which has something like 24 equivalent conditions for this property that you're saying to hold. So I don't feel that I can really add to that, yes. Yes.
So, but for positive, it would be description for positive definite matrix, like determinant of all the blocks being positive. Yeah, so I guess.
Exactly, exactly. And this is exactly where the signs alternate. Those are hyperbolic matrices, right? Exactly. And those are exactly, that's if and only if, right? This condition holds if and only if the Alexander-French inequality holds, right? You have Cauchy-Schwarz in the opposite direction. Yes. Such matrices are very useful. They appear, for example, in special relativity or in general relativity, right? As the sign, yes. Yeah.
Some connection with probability theory.
The short answer is no. Might be a little too simple. I mean, my background is not in geometry originally, and I got interested in this for unusual reason. But, you know, so at the end of the day, you know, the proofs of these things are very geometric. But these problems were stuck for a long time when studied by geometers. And I would say that despite the fact that actually no probability appears in this proof, the intuition that you have as a probabilist really guides you in how to think about these problems in a way that may not be natural for geometers. And you know, the connection which may not be obvious, but which was more obvious from the way I arrived at this problem than what is actually done in the problem, right? Is that, you know, in probability we study usually diffusions. Diffusions are very natural objects, right? And diffusions are very naturally connected to these, right? These quadratic forms, you can view them as quadratic. If you have not polytopes, but high dimension, you know, like general convex bodies, you can really view these as quadratic forms of certain very nasty diffusions on the unit sphere. This was an insight due to Hilbert. And so there is a natural connection between these things and the theory of diffusions on the unit sphere. Right? But you know, with diffusions, right? I mean, if you talk to an analyst about elliptic operators, you know, they will very often assume ellipticity, right? The diffusion coefficient is bounded away from zero. This makes all of the theory go through. But as probabilists, we can deal with all sorts of nasty objects, right? You know, we can have objects that are not elliptic at all, that are hypoelliptic. We can look at diffusions on fractals and other nasty objects, right? Singular, highly singular diffusions, right? So for a probabilist, it's very natural to consider diffusions on objects that are highly irregular, that are degenerates, that are singular, right? That are very ill-behaved. And it's exactly these type of singularities that turn out to give rise to the kind of strange equality cases that we have here. That's so in some sense, these mixed volumes can be viewed as quadratic formed associated to certain rather nasty diffusions on the unit sphere, whose state space is the unit sphere. And it's because these diffusions are highly degenerate, right? So they're not elliptic, you know, they're elliptic, but not uniformly elliptic. They're not elliptic, they're semi-elliptic, right? But because they're extremely degenerate and in general extremely singular, right? If you really had a non-degenerate case, you would have no interesting equality cases. But because of the degeneracy and the singularity of these objects, this is where the equality cases are coming from. And you know, in a sense, when you're coming from probability theory, where people work routinely with such objects, right? You are not so scared of this behavior, and one has tools to study them, right? And this is not the only result we have. For example, this result is for polytopes, and this was by far the hardest result. But where we started was not for polytopes. We started in this case of Minkowski. So Minkowski originally, he only had dimension 3. Right, so only one body, but this can be extended to the same method of proof can be extended to the case where all of the bodies are the same. So we'll call this Minkowski's special case of the Alexander-French inequality. And in that special case, we are able to settle the conjecture in complete generality, right, without the polytope assumption. For any convex bodies K, L, and C, we settled this. We did that before. And there, when you go to general convex bodies that are not polytopes, it's exactly these nasty singularities that show up. And the way we do it is we really define some sort of diffusions of nasty, you know, nasty object. They're you know, using things like Dirichlet forms, things that are very normal in probability theory to study singular diffusions. we introduce certain self-adjoint operators that are defined using this kind of theory, and we are able to study them and extract these kind of equality cases from them. So, you know, having such a viewpoint is very helpful, right? Right. But at the end of the day, you know, what really makes probability is that we don't just study the operator, but we also study the sample paths of the diffusion. And these things, of course, never arise in this situation, right? So at the end of the day, you do not really see probability. But being a probabilist, you know that you can work with these objects and that they're tractable, right? And, so maybe, I don't know if that explains it. Before this, you know, we started with a different problem, which was not the Alexander-Fenchel inequality, but the Ehrhart inequality, which is used in probability theory. This is for Gaussian measures. And there we used things much closer to probability. We used hypoellipticity to study the equality cases of those inequalities. And that was really inspired by probability theory and by tools that are developed in probability theory. And we used sample paths there. So originally, by coincidence, I was using these inequalities to prove theorems in concentration of measure, and I realized that the questions of the equality cases were open, and that they were open because everything is degenerate, right? And when Yair, my PhD students with whom this work is also, when he first started with me, we started working on this problem, and we realized that we could, using probabilistic ideas coming from degenerate diffusions, we could solve this problem. And there we really used probability theory. But then once we understood that degeneracy is actually the mechanism that causes these equality cases could happen, I started looking for other inequalities that have the same phenomenon, and this Alexander-Fenchel inequality is the first thing that shows up when you look in Google, right? And that's how I got into this problem. But at the end of the day, in this problem, the probabilistic method is further. Exactly.